Oh, come on! What train? It's like the NSF digital train. To be like, this is why we do conflict of interest. This is why we do conflict of interest. This is why, I'm not going to share my data with a foreign person when they email me asking for information. This is like,
Ready and
have like little...
Dave, ready and
Okay, I'm going to give like 30 more seconds.
Okay.
We got girl. You can tell like behind the camera. It's like natural quiet time. All right, everybody. Had a natural long conversation, so I'll take over. I'm happy to welcome Dr. Patrick Taylor here from NASA Langley, who's going to be giving us talks about sea ice and in the Arctic and its variability and causes. I first met Patrick, I think we discussed 16 years ago at my very first science meeting with the series science team for radiation. And I was telling Patrick that it was a great experience for me because after my talk, there was a huge debate between some top scientists about whether I was right or wrong. And I was just told by it that this is common to this. But I learned with Patrick from those meetings that scientists can have fun with science and we're not just weird science people. Anyways, Patrick comes from background from California University of Pennsylvania, where he got his bachelor's degree in 2004, his master's degree and PhD from Florida State University then in 2009, and ever since then he's been at NASA Langley doing research with the radiation group there. His talk today is going to be focusing on causes and consequences of the change in Arctic and the clouds and how they're responding to changes in sea ice. He has a nice background at Langley. He's received several recognitions there. The Presidential Early Career Award for Scientists and Engineers. He has received in 2013 the NASA Early Career Award, and as well as the Kavli Frontiers in Science Fellow from the National Academy of Sciences. He's currently the Deputy Science Lead for the NASA Arctic Radiation Cloud Aerosol Surface Interaction Experiment, or ARCSIX. He's the Principal Investigator for the Hampton Roads Coastal Resilience Project, and he's now the co-chair of the AMS Polar Meteorology and Oceanography Committee. You ever get to talk to Patrick a lot, you get to learn about more about sports, being active, and home brewing. He's actually been trying to convince me now to start back up that hobby.
Yeah, you should start brewing again.
Exactly.
You should.
But with that, I'll hand over to Patrick.
Thanks for the introduction. And it's a story for beer if you want to know how I became the principal investigator for a flooding project. I can tell you about that later, but that's true. It's not an accident. But so, before I get into what I plan to talk about, when you come into these presentations, you always want it to kind of be really clear and have everything buttoned up, but I would say this is much more preliminary results than anything, which is a great opportunity to get some feedback from everybody here. But I think some of the results are very exciting that I'll show you as we get there. But so I'm here to gather feedback and to learn. So with that, we know that our planet is changing. That includes warmer temperatures, more flooding, longer, stronger heat waves, more wildfires, rising seas, and that these changes that we're experiencing in our climate system are affecting human systems and natural systems alike. But these changes that we're seeing in our climate, aren't equally distributed across the globe and have strong regional fingerprints. And one of the places that are warming, changing faster than anywhere else is in the Arctic. So one way to look at that is here's an animation of NASA's GISS global temperature record, which began in 1880. These are 5-year running means, and your base period, these are anomalies from the base period, which is 1950 through 1980. And what you see is that, from the beginning of this time, the planet's warmed by roughly about 1 degree Celsius or so. But what you'll see is if you look at the top of the planet as we get more into present day, current time, we'll see this red cap that's forming. And that's your Arctic amplification signal. The Arctic's warmed by at least 3 times faster than anywhere else on the globe. And while these changes in the Arctic may seem somewhat isolated, although they do dip down into mid-latitudes and places for sure, we have to remember and realize that we are all connected to the Arctic, right? We live on an interconnected planet. And I wanted to take a moment here to talk about that a bit, because I think this message that the Arctic is changing really quickly is something that as a science community we get, right? But maybe what's not as clear is why we care so much about the Arctic. And it turns out, understanding the Arctic is more than just a fascination, right? The Arctic is home to a vast array of riches. These include oil and natural gas reserves, rare earth minerals, fisheries, and also these time-saving shipping routes, which I have up here. We know that global society relies on energy, and that's what implied here on the map on the left are these large areas of oil and natural gas resources that are located in the Arctic. These are becoming more accessible with warming and sea ice loss, and maybe even more attractive with additional warming for mining, essentially. So the Arctic is really becoming a key region in kind of geopolitics, more than it was before. Also, the Arctic has these untapped rare earth mineral resources that are important for our modern technologies. And underneath all that sea ice that we have currently in the Arctic on the right lies an ocean. And that ocean can be used as a food source. About 10% of the global catch of fisheries is actually from the Arctic, and that number is going to grow. And also, there are lots of companies and countries that are planning to exploit the potential shipping routes through the Arctic, right? In particular, in this red one here, this is your North Sea route here along the coast of Russia. And so currently most of the ship cargo that goes from Asia to Europe is coming via the Suez Canal. And that route takes about 37 days to get from Asia to Europe. But if we're able to use, if the North Sea route is open, is able to be used, that cuts down that time to about only 22 days. So it's like a 33% increase, more efficient route. And so with all of that in mind, using the Arctic and these predictions and projections of change in the Arctic are becoming even more important than they were in the past, when the Arctic is becoming now much more accessible and much more has global implications. Now, it's not just the sea ice, but the land ice in the Arctic is also changing, which you may have heard, and this also has implications that connect our planet. Here is some data from NASA's GRACE and GRACE follow-on, which show the Greenland ice sheet. We've lost a significant amount of ice, which you'll see here, mass around the edges, and gained a little bit in the interior due to increased snowfall. But since May 2002, you can see on the upper right-hand corner that the average mass loss that we've seen is about 269 gigatons per year. And to put that into perspective, that's roughly about enough water to fill about 120 million Olympic-sized swimming pools every year. So it's a lot of water. It fills the oceans, though. And in that time, Greenland has accounted for about a quarter of the global sea level rise that we've seen. But it's not just that average melt. Some years there's a lot more melt than others. And just to point out the 2019, really big melt year that happened right here, which was about 532 gigatons of melt that happened just in that one melt season. And that raised global sea levels by itself by about 1.5 millimeters. Or that's enough water to cover California in about 4 feet deep of water. So it's quite a lot of water that we have. And we know that these changes in the Greenland ice sheet, again, have global implications by influencing the thermohaline circulation potentially and contributing to sea level rise. So again, it's with that backdrop that understanding what happened in the Arctic is really, really critical. And these changes, the climate models tell us anyway, that these changes are going to continue, even if we consider the fact that some of you may have heard that the sea ice decline has kind of had this recent decadal-like pause where it's not dropping quite like it was before. But even in light of that, we expect that the Arctic is going to continue to change. It's going to continue to warm, which is shown here on the left. And these are temperature projections from Zach Labe using the CESM lens, the large eddy simulations. But we see that the general character of the changes that we expect are this warming throughout fall and winter across much of the Arctic, and this decline in sea ice, where we see that sea ice kind of retreats towards the north coast of Greenland and eventually kind of disappears. And so, this general character of Arctic change, right, is something I think we have a pretty solid grasp on, but there's still a lot of uncertainty here as to how fast the changes are going to happen in the sea ice, how fast and how much the temperature is going to warm. So if we ask the climate models that, a range of climate models, not just one, right, we get a very wide range of different responses. This one's not as quite as clear as I hope, but that's the challenge that we face, right? Humanity kind of wants to know, society wants to know, well, how fast is the Arctic going to change? And we need to provide that kind of that information as to how fast it would change as a function of kind of climate forcing, right? How much CO2 we put in the atmosphere and how fast is the Arctic going to warm? And to demonstrate that uncertainty here, what I have shown here is a plot of Arctic amplification factor. And so I'll use understand. But on the x-axis here is longitude, so the South Pole is on the left, North Pole is on the right. Each line here represents a different climate model, and on the left is CMIP 5, so the older generation models, and on the right is CMIP 6. RCP 8.5 and SSP 8.5 aren't the same, but for this, they're close enough. But what you see is that if you look at the amount of warming, Arctic amplification factor then on the y-axis is this ratio of Arctic warming, and here it's each latitude zone warming normalized by the global mean warming. So if there's a latitude this number's above 1, that indicates that that region is warming more than the global on average. And so if you look at the right-hand side of these plots, poleward of 60, you see that there's much more warming there. The amplification factor is much greater than 1. But we see across models, we have this range from about 1.75 to about 3.5, or getting close to 4 in CMIP 5, and we have a similar range in CMIP 6. So this range, as we have changed and supposedly improved our models, the amount of uncertainty in future warming in the Arctic is essentially the same. And if we put that kind of in perspective of some of the climate targets, like consider the Paris Climate Accord, the target is to keep global warming 2 degrees C or less. And so we consider a 2 degrees C global warming. This uncertainty range in Arctic amplification suggests that the Arctic, even if we were to meet the Paris target, the Arctic could warm anywhere from 3.5 Kelvin to 7.5 Kelvin, right? That's our uncertainty range. And certainly the Greenland ice sheet and the sea ice care about that 4 degrees Celsius warming difference. So it's a really, it kind of highlights the importance of trying to figure out, well, what is driving these changes in the Arctic and why are the models so different? So to do that, I think we do have a firm understanding of the processes that are important in warming the Arctic going forward. But maybe what we're missing is kind of the quantitative, detailed level understanding that's kind of required in order to understand that range a little bit better. So we've learned a lot about Arctic amplification, and I would say that this is a plot. We worked together on a review paper a few years ago on Arctic amplification. I think this kind of summarizes what we know about Arctic amplification and learned since Arrhenius first kind of published on it over 100 years ago. And we were able to break down kind of the general processes that are driving Arctic amplification into like 5 key concepts. So first we start with, and we can kind of put this together in a story where we increase CO2, right? So we increase CO2, that increases downwelling long-wave radiation, and that drives some local warming in the Arctic. And that local warming in the Arctic then activates a number of positive local feedbacks, the strongest of which is sea ice albedo feedback, which we'll talk about more. And then those positive local feedbacks then amplify the warming further. But it's not just that we have those local feedbacks, but we have a strong, stable atmosphere in the Arctic, and that helps cause that warming to be trapped near the surface. That warming then and the sea ice loss is really happening, it's focused in summertime, because that's when we have the most sea ice loss. And that energy then accumulates in the Arctic Ocean in summer. But we don't see the most warming in summer. As I mentioned a few slides ago, we expect to see the most warming in the Arctic, and we're seeing the most warming in the Arctic in fall and wintertime. And so that energy that's being accumulated in the Arctic Ocean in summertime is then kind of transferred by the ocean heat, uptake, into fall, where the most warming is actually happening. But then it's not, Arctic amplification is not just these local processes that are happening in the Arctic, but they are remote processes that are also really important. So as you increase CO2, the whole globe is really warming. And where this really comes into play with the Arctic is, there's still polar heat transport that's happening. But now, because the globe is warming, the character of that air that's being transported into the Arctic is changing. It generally tends to have greater moist static energy. So there's greater water vapor transport that's happening in the Arctic. And pretty much all climate models that look at this kind of show this. And that leads to this increase in moist static energy transport, which brings more water vapor into the Arctic, and then has a number of different effects which can help accelerate or feed back on some of the sea ice loss that we've already seen. And that's concept here number 5, which is these activation of the positive feedbacks by the remote forcing effects that are happening. And at various levels, that we've seen all these in different model experiments all operating. And I think where we need to go here is understanding which of these processes are responsible for that intermodal spread that we're seeing across the climate models. But with that, I want to kind of hone in. Oh, let me actually make one more point here before I. Well, no, sorry. That point's in a few slides. I'll get there. But I want to hone in here because I don't think maybe everybody sits and thinks about the Arctic quite every day like I do. So I wanted to say because this feedback, the sea ice albedo feedback, being like the most important one of these feedbacks, certainly the most important local feedback towards contributing to total amplification. I wanted to at least stare a little bit about a general animation to bring us all up to speed as to what's happening there. Right? So the surface albedo feedback is this process whereby, as we warm and we melt back the sea ice, the bright sea ice, we're uncovering more of the darker ocean underneath, right? The darker ocean underneath then is, I was hoping it would play again. Oh, there it goes. Is then as we uncover the darker ocean underneath, more of the sunlight is being absorbed in the ocean. The darker ocean, and then that warming that's happening then promotes more sea ice loss and then more uncovering of the darker ocean underneath. And that's this positive feedback loop that is the surface albedo feedback. But what's key about this is a couple things. One is that this ties the strength of this feedback to the processes that are actually contributing to the melt of the sea ice. And we'll come back to that in a second. But I also think it's important to point out that this movie makes it seem really simple, that the surface albedo feedback and the sea ice albedo feedback is just this Arctic fading from a bright white to a bluish color. That's actually not what you see if you go to the Arctic. And so a few summers ago, I had the opportunity to go to the Arctic and spend 8 weeks in Greenland. And what you actually see when you fly around the Arctic is not quite that very simple picture, but you see this very highly heterogeneous surface that is very hard to capture inside of any model, but particularly climate models. Or really the Arctic is fading from this very heterogeneous, you have these ridges across the sea ice, this is the land snow cover and the like, fades kind of to a brown time over here in the land, and you can see the distribution of melt ponds that happen through summer. So this highly heterogeneous surface that we actually see in the Arctic makes it a challenging picture, and is certainly responsible for a lot of those differences that we see across climate models. As we know, not all of those climate models that I showed, those different lines, not all the models still include melt ponds, for instance. Certainly in CMIP 5 they didn't. And as we move forward, more of these processes we represented, but some of those differences are really, so I guess I'm going too slow, the slide advanced itself, but some of those processes are not represented and causing some of those differences that we've seen. Okay, so with that kind of background of surface albedo feedback, I want to show this comparison of the feedback across models. And so one way we figure out and determine across all these different climate models, which here, each of these dots represents a different climate model, how much the different feedbacks contribute to the warming is we use what's called feedback diagnostic approaches. One of the most popular ones, like a radiative kernel approach, where you take the change in surface albedo, you run it through something like a radiative transfer calculation, which a radiative kernel is a simplified version of that, and then you get that energy change that the sea ice and surface albedo change is responsible for, and then you can figure out how much warming that equates to. And so that's essentially what they've done here. And so again, each of these different circles is a different model, and the red line here in particular is your surface albedo feedback, and this is for CMIP 6 models. And so you see on the x-axis is the total amount of warming that a model shows, and then on the y-axis is the warming contribution from each of these individual feedbacks. So each of the different colors corresponds to different feedback. And just focusing in here on the surface albedo feedback, if you compute these different warming contributions from the models, you see the largest range across all these CMIP 6 models is happening in the surface albedo feedback. I wish I didn't do that by accident. But you also see that as the warming contribution from the surface albedo feedback increases, the total warming increases as well. And so this is a very powerful approach to figure out or to have some sort of idea of what is driving some of these differences across models. But what I contend, and this is something that we had a lot of discussion at a workshop a few years ago, is that if you use these feedback diagnostic approaches, they're really able to tell us these differences, these energy differences. What they aren't providing us is the actual processes in the models that are driving the sea ice loss that's giving us these. So you can think of these different circles as different amounts of sea ice loss that the model's producing. But we actually don't know why the different models are giving us different patterns or rates of sea ice loss. that causal kind of link is where I think is where we need to go. And that was the outcome that was from a polar amplification workshop, which I co-led with Nicole Feldel and some folks with US Clivar back in January 2024. And that was one of the things that was really highlighted there. And that led us to take kind of two actions. One of those actions was kind of a direct recommendation out of that workshop, which is if we want to understand what's driving the sea ice loss across climate models in order to understand the intermodal spread, we can't do that with monthly mean output, right, from models. And so what we did was, after that, Nicole and I put together a proposal for the Ocean and Sea Ice Group as part of the CMIP7 data call, and we were able to successfully propose the causality to polar amplification opportunity. So in the next year or so, and this paper it just got accepted last week, even though it was submitted last summer, you can see the date, but we will have some from sea ice fields, atmosphere energy fields, as well as ocean model output from CMIP7 models. We'll have daily timescale high frequency output for a range of climate models associated with this opportunity. So this will allow us to explore what some of those factors are including, for instance, synoptic scale variability and the like that are contributing to the melting sea ice. And we can finally ask the questions, what are these differences in synoptic variability, cyclones, or atmospheric rivers that are driving sea ice loss and sea ice variability across the models? And we can ask the question, are the differences that way models are producing these and how models, sea ice is responding to these events, is that responsible for the intermodal spread and Arctic amplification? And you start to get at that causality. So that's one thing that I wanted to advertise so everybody have an idea of as we move forward. But kind of the second action that we took, and what I want to focus on for the rest of the talk is some analysis that we've actually been doing. Some real science, hopefully real science, that's preliminary at this stage, but hopefully, we're making some progress to understand specifically these questions. We wanted to ask the question, what is driving sea ice melt in the Arctic? And specifically we asked, why is some sea ice in a summer melting, and why is other sea ice in a certain summer surviving the summer melt season? Now, we don't look at this across models, but we put together with a sea ice parcel database a few years ago, which was published in Horvath et al. Actually, I think it's 2023. I think I have that wrong. But a sea ice parcel database. And what this is, I guess first, to answer this question, we thought it was really important for us to use a LaGrangian perspective, right? So you think about sea ice across the Arctic is really anything but stationary, right? It's kind of constantly moving all over the place. And if you don't track those sea ice parcels as they move and you just focus on an Eulerian perspective, you're going to convolve a lot of different factors of what's driving the sea ice loss in a specific spot. We want to understand, the sea ice parcel is moving around, what's causing it to melt or to survive the summer melt. And so to take that sea ice Lagrangian perspective, we adopt this database, which is kind of based on the NSIDC sea ice parcel tracking algorithm, which you can see right here. These are some example kind of sea ice parcel tracks across the Arctic. See some of them start and stop, some of them go the whole way across the North Pole, out the Fram Strait from the Pacific sector. And so with this algorithm, we're able to track sea ice parcels using the passive microwave satellite data as it drifts around the central Arctic, or the Arctic in general. And then what was unique that we did as part of this project is we co-located a number of different data products, satellite data products as well as reanalysis data products. So for instance, for sea ice properties, we co-located, we have series data products for radiation fluxes and albedo. We have biomass. The biomass data products is a kind of reanalysis sea ice thickness data set that's co-located with all of these parcels. We have passive microwave sea ice concentration. We have snow depth. The snow depth comes from what's called model LG. Model LG is a snow model that's forced with ERA 5 and MERA2. It's run separately for each, but precipitation, right? So we have reanalysis precipitation, and the snow model handles the snow that we get. We have lots of atmospheric state information for reanalysis, and a few flags such as cyclone flags to know if a parcel is being affected by a cyclone. And so with these different, with this kind of data set, then we're able to to really get at this question. Well, why do some of these parcels that are in here don't survive the summer melt and others not? So another, before I get into some initial results, we defined this this concept of sea ice parcel survivability, and it's kind of a really simple metric that we think, in the future could be really useful for, model evaluation, or at least understanding kind of, if we use this inside of a climate model to understand why different parcels melt and not. But to define this survivability, and it's simple: the number of parcels that survive versus the total number of parcels. And you can imagine you can cut this up based on a region, or based on a lot of different bins and a lot of different factors, which I'll show you some of those results in a second. All right, so what are some factors, just as a primer before I show you some of our results from this? What are some factors that we've considered that influence sea ice melt? We have, I think most obvious is sea ice properties themselves, right? The concentration of the sea ice, the thickness of the sea ice should certainly matter. The topography or roughness of the sea ice, the amount of snow on it, those are things that are really important. The sea ice dynamics, right? Whether the sea ice parcels, let me go back a second. Just to give you an idea, when I say sea ice parcel, this is what I'm talking about. So all of our parcels are, since they're based on the passive microwave, they're 25-kilometer footprints. And so these are, they use an image processing approach to kind of track these 25-kilometer kind of footprints as they drift around the Arctic. So this is, when I talk about a sea ice parcel, we're talking about 25-kilometer footprint that might have different flow size distributions inside, but it's whatever the NSIC algorithm kind of tracks around. But again, a parcel 25 kilometers. That's all right. So those parcels can undergo, right, sea ice dynamics, convergence and divergence within there, which may change the sea ice thickness distribution. So that's something that's a process that's important. The atmospheric conditions could vary, right? We could have different atmospheric winds or humidity or clouds could be different between these parcels. Surface that also influence the surface energy budget, and then also ocean conditions. Different turbulence or waves or heat flux could also, all these things can influence the sea ice melt. So the first result I want to kind of show is a bit of context, but also, we were surprised to find when we started digging into the literature on this kind of topic that I haven't found anybody else that's kind of looked at the survivability percentage. So first, I guess, let me show you these. Each number here for the different basins. The top number is the survivability for our decade 2010 through 2019 for multi-year ice is on the top, and the bottom is first-year ice. And we separate those two out because multi-year ice tends to be thicker. It also tends to be rougher. And the first-year ice tends to be a little bit flatter. And so there's lots of physical reasons to separate those two. But we see that, so generally speaking, so you can go around the Arctic, look at the different basins. But what we were surprised when we looked at the literature is this regional distributions that I'm showing you here of these different survivability percentages, these haven't really been published before. We couldn't find a lot of numbers to compare against what we're getting, right? And so one number that we were able to compare against was Kyle Armour et al. 2011 did a Pan-Arctic study using sea ice extent. So they used kind of a regional definition for this. And our regional numbers align pretty well with what they have. For Pan-Arctic, our multi-year ice survivability currently is about 74%, and first-year ice is about 26% on average. So we look at kind of the different regions and how they map into that Pan-Arctic numbers. We see the Central Arctic has a much higher survivability, right? Which makes sense. Gives us some confidence that our sea ice parcel database, we're doing okay. We find that 90% of multi-year parcels survive in the Central Arctic, and almost 70% of the first-year parcels survive. We can see there's much less survivability here on the kind of Atlantic sector of the Arctic, and higher survivability in the Pacific sector. But I think kind of the thing that was most surprising to us and to me when looking at this plot is this gradient that we find in survivability here in the Pacific sector. In particular, the fact that we have the Beaufort Sea here and the Chukchi Sea here have similar survivability rates for both multi-year and first-year parcels, but that the East Siberian Sea has a little bit higher survivability. And that gradient was surprising. We kind of, we still don't have the analysis that I'll show you for the rest of this presentation is starting to dig into that, but we'll see, we still have open questions as to why this gradient happens across the Pacific sector. All right, so we can take that's kind of the regional perspective, but I want to take a short break to give a kind of a finer scale perspective, because I want to highlight some of the importance of sea ice drift here, even though for the most part, the rest of the presentation, I'm going to ignore sea ice drift. But what you're looking at here is the density maps. So we've separated out all of our parcels for a given year into multi-year surviving, multi-year melt, and then first-year surviving parcels and first-year melted parcels. And then the colors here, these heat maps, are density plots. So we take all the parcels at the beginning of the melt season, and we find out where are the ones that survive located, and those are the reds. And then here, this is where the locations of the highest density of melted multi-year parcels. So what this kind of picture shows is places where there are sea ice havens and sea ice graveyards. So where do we lose multi-year ice, and where do we keep it? So multi-year ice here is these haven, here we'll call it, is off the north coast of Greenland and Canadian archipelago. And this position has a lot to do with the transpolar drift of the sea ice, right? As sea ice comes across via the transpolar drift and crosses the North Pole, kind of these lucky surviving parcels end up getting pushed up against the North Greenland coast and the Canadian archipelago, where there's really favorable conditions for survival. The unlucky multi-year parcels end up being the ones that come across the transpolar drift and get kind of exported out of the Arctic here via the Franz Strait. You can see that highlight there. And then we see that a lot of multi-year parcels also melt when they get kind of ejected or exported out of the central Arctic into the Beaufort Sea. So we see a lot of multi-year parcels that are being melted there. From the picture for first-year ice is slightly different. The melted first-year parcels tend to have much more of a zonally symmetric-ish kind of distribution, where they melt, where they survive, is very strongly correlated with latitude, right? Solar insolation. But what we were surprised to find, and again, we still don't, as I said, we still don't fully understand why we have this kind of bullseye. This is the first time we've seen anything like this, where there's this region of the East Siberian Sea where first-year parcels really have a higher likelihood of surviving. And so one thing we want to start looking at is what is special about this East Siberian Sea, what that allows these first-year parcels to survive. So we want to start asking the question then, I've showed you these spatial patterns of sea ice survivability. Where do they come from, right? And so there are kind of two approaches we want to take here. One being, the question is, well, maybe there's different regions of survivability because the regional mean properties are different, right? And so to look at that, what we've done here in our scatter plots is we have each dot here represents each one of those different basins. So the central is in blue, the Beaufort here, and the Chukchi in gold, East Siberian Sea in pink, Laptev Sea in purple, and then the Greenland Sea here in green. You notice again, I won't say a lot about the Greenland Sea because it's kind of being in the Franz Strait there, it kind of behaves very differently from anything else. And we kind of generally have, a lot of folks have kind of ignored the sea ice in that region because we know it's going to melt anyway, because it's in the North Atlantic. That doesn't mean it's not important, but maybe I won't talk much about it after this. But so what we have here is survivability on the y-axis, regional mean survivability on the y-axis for the decade, and then different sea ice influencing factors for regional mean values on the x-axis. And so first we can look at kind of the obvious one, which is we think that if sea ice is thicker, it should have a higher survivability. And if you look across, all the dots, right, maybe you see the Central Arctic has thicker ice, so it has a higher survivability. But what we're surprised to find, again, this gradient across the Pacific sector, where, the East Siberian Sea has a much higher survivability of the sea ice than the other basins, but they all have roughly the same sea ice thickness. So sea ice thickness doesn't seem to be telling the whole story about why some parcels survive. It's not just the thicker ones that survive. And so if we look at some of the properties that seem to be more important, we see that the mean sea ice concentration across the regions, so the regions that have a higher consolidation of the ice seem to be correlated positively here with survivability, as well as the mean snow depth, right? We see regions with more snow depth tend to have higher survivability, especially across, again, the really interesting ones are these to me anyway right now for this work is these three dots right there that represent the Pacific sector. There's the East Siberian Sea, the Beaufort and Chukchi Seas. And so this gives us a hint that the regional mean sea ice properties, specifically sea ice concentration and mean snow depth, are two really important variables for this. But we wanted to, again, continue taking a deeper look, which is we wanted to understand what properties between the surviving parcels and melting parcels are kind of different, right? So we wanted to compare the properties of these two to be able to understand, like, are there specific distinguishing factors within each of these basins that are different between surviving and melting parcels. And so we do that in particular using this an annual cycle composite approach, and I'll show some of those in a second. But what's really useful about the annual cycle approach is that it allows us to look, again, across the entire growth, freeze up, the growth, and melt season to be able to identify if there's anything during the entire year that's influencing survivability, right? Because there's lots of hypotheses out there for preconditioning by snow or in the spring that could support sea ice parcel survival. So using this annual cycle approach allows us to kind of identify those and see if they're there. Before showing you some of those difference plots, I just want to provide some context and a bit of a sanity check of our sea ice parcel database again, because as I mentioned, and we have the same questions about the reliability of it, because again, it's a lot, besides some of the satellite data products, there's a lot of reanalysis in there, and we know on the whole, reanalysis is a little bit uncertain in the Arctic in general. So what I have here, what we plotted here are separately for multi-year ice and first-year ice. We have sea ice thickness in these blue colors. We have sea ice concentration in the yellow and red, and then we have snow depth here in the greenish colors. And we see this is the general annual cycle. And the first thing that you see is, as you look here, if we focus on both thickness as well as snow depth, this is October here, so we have fall sea ice freeze up in the fall, and then as we go throughout the season, both thickness and snow depth kind of slowly increase, accumulate, which is good to see until you have this plateau in late spring, late in springtime, and then once we get to melt onset here around June timeframe, you see the snow disappears and the thickness declines, and so these are all in line with what we'd expect. One interesting thing that I wanted to note before, but I forgot, which is the line for sea ice concentration for first-year ice is a little bit funny. So you see that throughout the winter time, when you would expect sea ice concentration of parcels to increase, we actually see this decreasing of sea ice concentration. And the reason we do is because throughout the winter season there, we're actually forming new parcels. And the way the algorithm forms new parcels is a new parcel is identified when sea ice concentration reaches 15%. So every time you form a new parcel, you're actually adding a new parcel that has a 15% sea ice concentration. So as you form the new parcels, you're actually going to reduce the average sea ice concentration for these first-year parcels. So that's kind of what's happening there. With that one, white looks a little bit odd. But I know I want to keep moving to some of the other stuff and not dwell on some of this, but I guess I would also show some of the annual cycle of the radiation values as well. So here again, we have long wave downwelling radiation in the blues. We have the temperature in the green colors, and we see that as you start in October, you have temperatures in long wave downwelling radiation kind of decreasing, reaching kind of a winter time minimum value, and then as we get to summer, the yellow and red here are shortwave net. So you see the solar insolation is increasing, and the shortwave net becoming positive, warming temperatures until we get summer melt and then it flattens out. And the pink colors there is we'll talk more about that as we go forward, but that's showing the albedo of these sea ice parcels. So we see that we start with high albedos in spring. As we start to melt and form melt ponds, we get lower albedos that kind of are lower for first-year ice and multi-year ice. And so again, all these are consistent with the in-situ field observations that we've compared it against. And so again, we have confidence that at least we're representing the evolution of sea ice parcels we would expect in these data products. All right, so to dig into some results, as I mentioned, we have how we were looking at identifying which properties are different between these parcels that survive versus parcels that melt, is we compute these annual cycle composite plots, like I showed on the previous slide, for these, for instance, parcels that survive and parcels that melt, and then we take a difference, right? And so what you're looking at here are a couple examples of those annual cycle composite plots and those differences. For here, this is sea ice thickness for first-year parcels, and I have long wave down and surface albedo. And I just showed, here's just a few examples, because I don't want to go, there are many, many of these plots, and we don't want to go through all of them today. But I showed you as an example of kind of the steps that we went through in order to identify which processes are most important. I'll spend more time on sea ice thickness and surface albedo later, so let me highlight quickly here like the long wave down. So again, what we're looking at here are differences between surviving minus melted first year parcels. And so kind of what we're looking at is we're trying to see, like, are these numbers very far from zero, right? If the number is zero, that means there's really no difference in the downwind long wave radiation between the surviving and melted parcels. And so we do see, like, well, this green line for Greenland always sticks out. It's a very it's a very dynamic region. But if we look at, I can point out the Central Arctic here in blue. Darn it. At least it keeps me awake too. But we look at the blue colors here. This is the Central Arctic. We can see that, you know, there are these differences that maximize here. Sorry, this is the axes actually are different. I messed that up. But maximize in winter time here are the largest differences, where on average the downwind long wave radiation for melted parcels tends to be greater than for surviving parcels, which is why this is negative. So we see there's this regional relationship here. But for a lot of basins, in particular, this is the Beaufort Sea here and the East Siberian Sea and the Laptev, we don't really find any differences in downwind long wave radiation for the surviving versus melting parcels, suggesting that, you know, that the atmospheric forcing, and we find the same thing if we look at the cloud long wave radiative effect in winter as well. And so these long wave forcings don't seem to be a really strong factor for determining sea ice survivability. And so, again, we looked at a whole bunch of those, but I want to just summarize a few of those here before we look at a couple of them in more detail. So we found that the variables that seem to be most important in determining survivability are sea ice thickness plays a role in some basins, sea ice snow depth, sea ice concentration, surface albedo, and shortwave net, as well as surface temperature, particularly in winter. And so you might notice these are a lot of sea ice properties themselves, right, that seem to be more important. Whereas, you know, some of the downwind long wave and long wave cloud radiative effects throughout winter aren't really playing a large role outside of the Central Arctic, which I showed. So those peripheral seas, it's not so much what the atmospheric radiation forcing seems to be doing. All right, so I want to highlight here and go into more detail, because I think as we get into sea ice thickness story, I think there are some things that will surprise us for sure. So first, I mean, the primary takeaway that we have here is, while sea ice thickness does seem to be important, there are some regionally dependent relationships with survivability that were a bit surprising. So let's talk about those a little bit. So here, we're back at these annual cycle difference plots, where again, it's survive minus melted. So here, if you look at these positive numbers, means that the thickness of surviving parcels is greater than that for melting parcels. This gray line is the Arctic domain average, and then each of the other colors corresponds to a different basin. And so the first thing that's you know, we see that in the Central Arctic in particular, for multi-year ice and for first-year ice, that the difference in thickness for surviving and melting parcels kind of grows, where as you go through the winter season, the surviving parcels tend to have more thickness growth, right? And you see that's positive, and then it plateaus here a bit, but both for first-year and multi-year in the Central Arctic. But again, if you look at some of those, peripheral seas, and in particular, I mentioned East Siberian Sea and the Chukchi Sea here in the pink and gold, respectively. All these difference plots throughout most of the year, until you get to the end of summer, are really close to zero. So we would say that in these basins, thickness isn't playing a large role, which was really surprising to us. And also, the same thing is true for first-year ice parcels. So you know, this says that thickness isn't significantly different in every region for these different parcels. So these are just the annual cycle kind of averages. We wanted to look at look at this from a different perspective as well, just to make sure that wasn't kind of, you know, we were missing something a bit on this. And so what we also looked at is, for all these parcels, is we can look at the distributions within these bins, so sea ice thickness. So here, this is for the central sea ice thickness, and again, we have our same 4 bins of sea ice parcels, multi or first year, survived and melted. And before we go to the other basins, you know, I would say this is what we expected to find going in for all of the basins, where surviving parcels, you know, there's the distribution of thickness, and we picked May 1st here to show this plot, just because that's like the pre-melt onset sea ice thickness. But we see that for multi-year and first-year survived parcels, the whole distribution tends to be shifted towards these thicker parcels. But as you go to the melted parcels here and the red and the golden color here, those distributions are shifted to the left, suggesting that there's thinner sea ice melts and thicker sea ice survives. And again, this is what we expected to see here for all the basins. But when you look at the other basins, here is the East Siberian Sea, and these are all peripheral seas, right? The Beaufort Sea, you see some shift where the Beaufort Sea does have some thick multi-year ice that's transported in from the Central Arctic. But here in the Chukchi Sea, in general, and you see the same thing if you ignore the multi-year survived ice, but these other distributions seem to be all on top of each other, right? So there isn't really, the distributions of sea ice thickness for the different basins kind of are somewhat indistinguishable from each other, suggesting that there's something other than sea ice thickness that's determining whether these parcels survive or not. Another interesting feature in this distribution is specifically in the Chukchi Sea, there's some pretty thick parcels here that end up melting, but all these end up melting essentially here at really thick, the high thicknesses. So we can also do this a bit more directly, right? And we can bin our parcels by sea ice thickness, and then we can, within each of these bins, which we use our half meter, and we pick half meter because, well, it's a nice round number, but also half meter thickness is roughly about the uncertainty in the PIMS data set as well. So we pick those half meter thick bins, and then we directly compute the survivability rate within each of these regions for the different thickness bins. Right, now first we look at, let's look first at this blue line in the central and the black line here, which is the Arctic domain average. And I guess we see what we would expect to see, right? Which is as you increase the ice thickness, your survivability rates, increases, right? As you go towards thicker and thicker values. It's a little bit larger for the central as it is for the Arctic average, because the Arctic average is bringing in the basins. And you see roughly a similar behavior for the first year ice, even though you have slightly lower survivability rates. And so this allows us to say, oh, okay, yeah, we see that relationship, and we know that like 1.25 meter sea ice has roughly about a 20% survivability rate, whereas if you can get to like 2.5, Arctic domain average are around 80% survivability rate. But if we look at some of these other basins, and I think, again, I like to pick on the East Siberian Sea because it's kind of the outlier in some of this. If we look at this pink line here, and the multi-year works the same as behind me, but you see if you look at about 1.5 meter thick ice has roughly about a 50% survival rate. But if you go, in this basin, if you go thicker, right, we start to see that the survivability decreases. So in a couple of basins, and the Chukchi Sea is the same way, where we see that the thicker ice actually is more likely to melt than the thinner ice. And so there has to be something going on there, right? That's strange. And I have a slide on this later, but I think this relates to the role of ocean heat flux through the Bering Strait, as well as the fact that the ice is moving around. And some of these thicker parcels end up being unlucky and getting drifted into a place where there's more of kind of energy input. But the other thing I want to point out that I think is something that we'd like to explore further, especially when we think about as a climate change indicator, is we're identifying this thickness that we call kind of a 50-50 thickness. This is essentially the thickness of sea ice that has a 50% likelihood of surviving the summer melt season. And so when we use that for the Central Arctic, this blue line, because you see you can't do that for all the basins, because some of the basins don't have 50% likelihood. But for the Central Arctic, you can do this, and for the Arctic as a whole. And so if we look at the thickness that has a 50% chance of surviving, we get about 1.65 to 1.7 meters thickness. And we have it's roughly a similar thing here for first year ice in the Central Arctic, although it's a little bit thicker for the Arctic domain as a whole. And we think, as the Arctic continues to warm, this 50%, this thickness at which has a 50% likelihood of surviving is likely to become, thicker and thicker values. And tracking how that's changing in time could be really useful in understanding, tracking the changes. All right. So now let me shift gears slightly in the time, and let me try to finish up in a couple minutes here, but I want to shift to snow. Because snow has a really, again, a surprising relationship. So what we find first is that snow depth does increase the survival rate, right? But it doesn't do so in like kind of a linear fashion. Rather, there's a threshold. So if you add a little bit of snow, your survivability rate tends to increase pretty quickly. It depends on the basin, I'll show you that. But then it get to a plateau place where no further snow actually increases survivability any farther. So there's kind of a threshold behavior here. And that depth of snow ranges here depending upon whether you're on first-year sea ice or multi-year sea ice or which basin you're in. So since I'm a little bit behind, let me just skip to this one and show this story, which is, so now we're back on those survivability plots. We have survivability on the left axis, and I'm sorry, but I forgot I need to change out this axis and update this, so these depths are a little bit off. But just as a note, this is 45 centimeters, and this is 25 centimeters, even though that axis is wrong. But what we see here, again, in terms of survivability versus snow depth for our bins, is that, again, increasing snow depth does increase survivability, right? We see that clear. And that was somewhat surprising because there are competing effects of increased snow depth on sea ice survivability and sea ice thickness, right? Throughout winter, if you have a lot of snow on sea ice, it actually doesn't, the sea ice isn't, the insulating effect means that the sea ice isn't growing as quickly. But then in summertime, the increasing snow depth, having more snow actually increases the albedo of the sea ice. And so they have these competing effects. So it wasn't clear going in. There's always been questions over the years about, is snow a friend or foe of sea ice? And what we're finding is that it is a friend of the sea ice and does increase survivability here. And so you can see that, but the other thing I want to point out is if we go back to these different basins, the ones I've been pointing out, like East Siberian Sea and Chukchi and Beaufort, we do see the same behavior where as snow depth increases, we have an increase in survivability, but it reaches a point where it flattens out, and that point depends on which basin you're in, right? There's something different about how snow is impacting the survivability of these basins. The Chukchi Sea reaches it here right around 25 centimeters, and the Beaufort Sea here is a little bit longer. And there are larger error bars that you can see in the dashed lines in the Beaufort Sea. But, so, and the last one I wanted to touch on here is the sea ice story, but recently we've realized that the impact of surface albedo change is very much tied to the snow cover, where we're finding parcels that have greater snow cover tend to have a smaller early summer decline in surface albedo, and so which results to a smaller net shortwave radiation early season, and so a slower melting in early season. All right, so with that, I know I'm really close on time, so let me say two things that I want to close on, one on sea ice and then one on snow. One is with sea ice, I mentioned those really, that behavior in specifically East Siberian Sea and the Chukchi Sea, which shows greater thicknesses actually have lower survivability. And we think what that means is that there are both these gradients that exist in energy inputs in the region, right? So if you redistribute the sea ice, you can melt them differently, specifically because there is enhanced heat transport through the Bering Strait. And then also that the fact that, thickness doesn't seem to matter in these regions kind of suggests to us that there's kind of enough, on average, there's enough heat around to melt any of the parcels that we're seeing with these thicknesses, right? And so the other thing I want to mention, and this one just rehashes what I said, but I wanted to kind of leave you with a couple kind of hypotheses and ideas we're going to dig into about what's happening with the snow, right? So the first thing that we found is we have snow, depth increases survivability. And what we're finding, looking at more relationships in the data set that we have, is that greater snow results in a less early summer shortwave net radiation, so less energy going in, and a slower summer albedo decline, right? But secondly, then we find this threshold behavior. And so in some cases, it either plateaus, and you probably noticed in some of those, like the line actually starts to go down, where at even higher snow depths, you actually reduce sea ice survivability. What we think can be happening there is, well, there seems to be the saturation effect of the albedo, right? More snow doesn't necessarily mean brighter albedo in summertime. And in fact, there could be a feedback here where you have more snow results in more meltwater, and that could then lead to more melt ponds that are then helping to kind of offset some of that increased albedo effect that we see from greater snow depths. And then lastly, just more of speculation as to what could be happening with the regional variations in that threshold behavior I mentioned. There are certainly differences in potentially roughness and sea ice topography between those basins, differences in snow properties and snow metamorphosis that happens, and also then differences in your atmospheric forcing, right? The air masses that end up being advected over the East Siberian Sea could be coming more from Siberia, which could influence more snow, and a different snow. It's telling me I'm done, but the other basins are likely to have more of a moisture influence from the Pacific Ocean as well. And so these are some things that we're thinking about right now, but thanks for your time and attention. Sorry, I talked longer than I intended. Thank you, Patrick. We'll open the floor for questions, and as usual, we'll open to students first, and then after that, we'll for everybody.
Yeah, that was a great talk. I just have kind of a very first order question when it comes to sea ice. It's not something that I think about a lot. But when I was looking at your intra-annual plots, and you're kind of looking at, mapping out things like sea ice thickness or just conditions that are favorable for sea ice growth that happens in that wintertime versus in the summertime is when you're starting to get that rapid melt. Keeping in mind that over time, like we're overall seeing greater reductions in sea ice. Can we attribute some of that to whether that's happening mostly from increased melt in the summer or decreased kind of accumulation and favorability for sea ice growth in the winter?
So I mean it's a bit of mix where we are seeing if you look at trends in sea ice extent, right, the most declining is happening in September. But there are declines that are happening. Maybe I'll do that. Otherwise, there are slides that I didn't intend you to see. You might see. So there are declines that are happening throughout all of the season. But the declines tend to be greater in summertime. In part, some of that though is happening because there's a priming that's happening throughout the winter, where the sea ice isn't growing as thick as it used to be. And so it's a understanding pointing to the exact causality in this sea ice story, I think, is a little challenging because it's kind of the whole annual cycle and how what happened the previous summer kind of feeds into what happens in the winter. And if you have less growth in the winter, it could precondition you to have more summer melt. And so there is memory in the Arctic system that comes from the sea ice. And so it's kind of like both the lack of the lack of growth, or I don't want to say lack of growth, it's growing, the sea ice is growing in winter, it's just not growing quite as much as it used to, is contributing to the declining trend of the sea ice, but there's also more melt that's happening in the summer. And part of it's because of the less of the thing. But also the ocean temperatures are warmer than they used to be, and the kind of environment isn't quite as conducive to keeping sea ice around.
Good, thanks.
Yeah.
Hey Patrick, for a great presentation. I have a clarification question for the survivability metric first. Is it defined using the LaGrangian approach so the movement of the sea ice is fed into the survivability as well, like how the sea ice is moving?
Well, so so yes, in that we attract the sea ice parcels around, and essentially it's a 1 or 0, right? If that parcel's around at the end of the summer, it's a 1. If it's not around at the end of the summer, it's a 0, right? And so it's really just that is just using, I guess, the NSIDC parcel tracking database. Does that parcel, as it's falling around, make it through the summer melt or not?
Yeah, so based on that, the results we're seeing for the Beaufort region, I was wondering how the Beaufort gyre circulation itself contributes to the locations you're finding for survivability, because it's not necessarily maybe melting, but it's just getting pushed
right
around the end of the season, and that's why you end up with the right side, like the East Siberian Sea being surviving, is that it's just getting pushed over there, and then the rest of the sea ice is just being pushed, melts, and
right.
the western.
No, I mean the drift definitely plays a role. Parcels, there are parcels that get lucky and they get moved into a place like that's more conducive. We haven't looked at more detailed about what the Beaufort gyre is doing in particular, but how we started to look at this is we've taken some of these plots and separated out parcels that stay in their basin of origin versus parcels that leave their basin. And if you're a parcel that goes from either the Beaufort or the Chukchi or the East Siberian Sea and you get into the Central Arctic, your survivability rate increases. It's just that, but these relationships in general stay, survivability increases because you drift into a place that's more favorable. And so, I mean, that's the drift in particular and exactly how to take that into account here is a little bit more a tricky thing. So that's where we've been able to look at the statistic. The story stays similar for both sets of parcels. It's just that when you go into the Central Arctic, your survivability jumps up. Your likelihood of surviving jumps up. So how to take that into account is something we're playing with. But so far what we've done is parcels that stay like in the Beaufort Sea, we just look at those ones. And if you leave the Beaufort Sea after a year, then we're not going to look at those and compare how those results vary with what I showed. And they're roughly consistent if a parcel stays versus it leaves. But
Thank you. It was a great talk. But I'm just a quick follow-up on Ludra's question. It's mostly curiosity driven and just very mad about it. But does it so happen that you have a sea ice and it breaks, and so now you have, and that affects your metric because now you have two of them, right? And that would affect the number of so it survives, but it increases the number of sea ice blocks that you have. Does that make sense?
yeah, so I think in let's say reality, that could happen. But when you think about so how the data products put together with this image tracking approach is they take consecutive images and they kind of match them to one, and so, or they match them between successive images. So if the sea ice parcel starts to break up and look indistinguishable, it certainly could influence that. And I think we need to think more about how those uncertainties could influence these results. But I think, well, that does happen, but this algorithm wouldn't classify them as two, though. I guess in that's again something that I think we need to think harder on. But if you start to break them up, like that is a realistic process with the divergence of the parcels. I mean, at some point, once the sea ice concentration drops below 15%, it'll cease to be a parcel. So if the process kind of breaks it up that much, you would have 0 parcels instead of 2, I think. Does that make sense? I mean,
Yeah, but definitely.
I have a question regarding the snow depth investigation that we did. I'm wondering if it will be possible to do to like parse the effect of thickness, ice thickness, and snow thickness at the same time, and see if you have like specific effect that happen for thin ice and high snow, or like large ice and thin snow, or something like that.
yeah.
Have you done that? Are you doing that?
We have started to do that. So the challenge with working with ice parcel database is that there's a lot of parcels and there's a lot of maps you can make. But you're right, like this database, to be honest, that's partly what is struggling with using the database. There's a million parcels in there and a whole bunch of different ways you can cut it, and so that's been a challenge. But yeah, we started, so we haven't made like, I can envision like these 2D kind of joint histogram kind of things. We can have heat maps and you can look at, thicker parcels, are in this quadrant or with more snow, vice versa, like what you're talking about. I think that is definitely something that we've thought about and want to do. We've looked at it in a slightly more simpler way, which is just using those same kind of binning approaches and looking at as different thickness bins, what's the snow depth in each, and we do find that thicker parcels tend to have more snow on them. And so that's true, but I do think that there could be these regimes that exist in here that we can explore that could be really important, that we could explore further to see if there are more gradations than kind of, we've looked at it in kind of a simple way, but yeah, that's a good direction.
Okay, Leo, and then we'll head over here.
I'm interested in that section of the Arctic Ocean, the East Siberian Sea, that was more favorable to survivability
Yeah.
of your first-year ice. I'm wondering, have you looked into your vertical transport processes like coastal upwelling or downwelling in that area, given that that's kind of where your boat and gyre spinning and your transport grid is also kind of cost?
We have not, but we'd love to chat about that. Because, I mean, one, I guess, shortcoming of this is this database is that when we first made it, we didn't bring in any ocean fields, and we tried to get money to add them, but that proposal wasn't selected. So we're still gonna try again, but I would love to chat more about the ocean role, because I think the ocean plays a big role in what's happening right here. I do, so yeah, it's a great question.
Yeah, thanks. I was just curious, going back to some of your first graphs.
Yeah.
What accounts for the significantly higher warming rates in the Arctic as opposed to the Antarctic latitudes?
Okay, so I think I just showed the Antarctic. So partly it's from the processes that are important. The same processes are important in both, but at different distributions. For instance, in the Antarctic, the moisture intrusions or atmospheric rivers, that moisture transport seems to be more important there. But in general, the surface albedo feedback, the melting of sea ice, and the increased absorbed energy and warming from that is much stronger in the Arctic than it is in the Antarctic. And also the lapse rate feedback is more important, has a stronger effect in the Antarctic. So those are the two things that are driving more Arctic warming. But from a that's kind of like at the feedback level, but the causal level, I think something that has to do with why those things are important is the fact that Antarctica has there's like a continent in the middle with ocean around, and the sea ice regimes are very different there than the sea ice that we see in the Arctic. And so I think partly of why the Arctic is more sensitive also is because it has the isolated basin with sea ice. It's not quite as deep, and so the sea ice there is just decreasing faster because it has a different nature. So I think while the surface albedo feedback is stronger there, I think the reason it's stronger there is because the sea ice and the ocean basin themselves are different between the two.
I'm curious about the role of ice mechanics. So you have two accumulation zones. Can you get them basically from currents topography and thermodynamics, or do you have to somehow, sounds complicated, take you kind of, when they run into each other, they stick, or if they're in certain patterns, they can lock, or ride up over each other, or pressure ridges and all that stuff to stick together. Do you have to take account of something like that, or it works pretty well anyway without that?
So, all those things are important to consider when you want to try to explain what's happening or how the thickness is changing. But from the parcel database perspective, we're just tracking, unique images, and so for that, it doesn't matter. But the biomass, the sea ice thickness, biomass would take those into account, so that would be represented as part of the thickness data that we've integrated in. So certainly that's all important, and that's what's happening off the north coast of Greenland and Canadian Archipelago.
So you don't have to worry how that happens.
We don't have to. Now, it's possible that there are, and likely that there's, biomass isn't perfect, and so that process could be not well represented in there, and then that would be represented as, our sea ice thicknesses here. And so certainly more sea ice thickness validation data for biomass is something that we would want. But yeah, so those, we don't have to, our analysis doesn't have to, we're not concerned with those, but they certainly would influence, if biomass changed as parameterization, we would have different thickness distributions likely.
Okay, one more, anybody? Going once, going twice. All right, let's thank Patrick one more time.
Thank you.